In this lecture, we'll talk about a problem in the short list of the IMO 2009. This problem is a problem number 5 in the number theory sector. It was provided by Hungary. The statement of the problem is as follows: that p of x be a non-constant polynomial with integer coefficients. The problem asks us to prove that there's no function t from set of integers to set of integers such that the number of integers with the n-fold application of t to the integer is the integer itself is equal to p of n for every n greater or equal to 1. Use somewhat fancier language, we can say that for any function from the set of integers to set of integers, the number of fixed points with respect to the n-fold application of this function t with dependence on n cannot be a non-constant polynomial in n. So that is basically what this problem is saying. Now let's talk about the idea of the proof. The idea is that we let a of n to denote the set of the fixed points with respect to the n-fold application of t. And we will look at the cardinality of a of n. Now suppose the cardinality is equal to some p of n for any n positive integer, where p is a polynomial with integer coefficients. Then we want to show that p has to be a constant. So this is our goal. The trick here is to break down this set a of n into a disjoint union of sets, and we will use prime numbers, congruence, and some properties of polynomials to conclude that this p has to be a constant. I will show you this trick. But this is basically the rough idea of the proof. The proof goes as follows. For any positive integer k, we let the set of the following integers. The kth-fold application of t applied to x is x. But t of L applied to x is not equal to x for all L greater than 0 less than k. Namely, this k is the smallest positive integer such that x is the fixed point of tk. Now we look at all such possible x. And you can call it a convention. The convention is that b of 1 is a set of fixed points of t. That's b of 1. Now we're going to make the following claim. We'll call this claim number 1. A of n is a disjoint union of B of k over all divisors of n. It's not hard to verify this claim. So let's check this. Indeed, this direction of containment is very easy. This is because if tk applied to x is x, for some k divisor of n, then Tn of x must also be x. Because this is like when you apply this tk for n divided by k many times. So you still get x. For the other direction, you might want to think a little bit harder. But the trick to prove this direction of containment is also somewhat common in algebra and number theory. For any x in A of n, let k be the smallest positive integer such that tk of x is equal to x. And we will show that k divides n. Now let n be equal to ka plus q. For q from 0 to k minus 1. This is a standard Euclidean division. This q is the remainder for this division. Then you look at tq of x. tq of x, by this equation and the fact that tk of x is x, this is equal to tka plus q of x. And this is Tn of x, which is just x. Now since k is the smallest integer, smallest positive integer, that does the job of fixing x with tk. We must have q equal to 0. So k must divide n. So now we have proved both containments. Now here we should know that this union is really a disjoint union. This is simply by definition. The definition tells you that B of k1 and B of k2 cannot be equal if k1 is not equal to k2. So the set of integers in one bk are completely different from the set of integers in another bk. Hence, we have proved this claim, number 1. And as a result, if you look at the cardinality of Fn, it will be the summation of all the BFKs where K divides N. So this is a result we're going to use later. Now we're going to make an observation on B of K. We'll write this as a claim. Claim number 2. We observe that K divides the cardinality of B of K for any positive integer K. The idea of the proof is that we're going to break this B of K into disjoint orbits. With each of which having cardinality precisely equal to K. So K must divide the cardinality of B of K. So that is the trick. Now let's verify this. Indeed, for any x in B of K, any aj from integers 0, 1 through K minus 1 and we assume I is greater or equal to j. Now if Ti of x is equal to Tj of x, then Ti minus j applied to x is equal to now because this x is in B of K, so it is a fixed point of Tk. So it doesn't matter if we replace x by Tk of x. And now we switch the order of ijk here. We pull out Tk minus j and apply this to Ti of x. Now this guy will be equal to, because Ti of x is equal to Tj of x. So this is equal to, and j cancels with negative j. So this gives us Tk of x equals x. But observe that this I minus j, because I is greater or equal to j, this I minus j is between 0 and K minus 1. But K at the same time is the smallest integer such that Tk applied to x is x. And now you get something smaller that forces that I minus j is 0. So since K is the smallest, I must be equal to j. Hence, for any x in Bk, x, T of x, Tk minus 1 applied to x are distinct. So what we are proving here shows that those K elements are distinct. Now, for any x and y in B of k, we look at the orbits. The orbits Ti of x from I equal to 0 to k minus 1 and Tj of y j from 0 to k minus 1. The observation is that those two things are either identical or disjoint. Do you see why this is true? This is true because if it happens that Ti of x is equal to Tj of y for some I and j, what can we do? We can keep applying t. We keep applying t. And it follows that those two sets of k element each must be equal. Okay, so those two orbits of t are either identical or disjoint. And that tells you B of k can be partitioned into disjoint sets represented by this orbit of t consisting of precisely k elements, so each of which has cardinality k. But don't forget, this B of k, by our assumption, is a finite set. Why is this B of k finite? That is because it's a subset of A of n. A of n is finite. A of n being finite is not something from the definition of A of n, but from our assumption that the cardinality of A of n is P of n, a polynomial. This value P of n must be finite. So this is whenever k divides n, and this is finite because it is assumed to be this polynomial P of n. Assumption. So k must divide B of k. And we are done with the proof of our claim number 2. Now we have proved the following 2 claims. Next, we are going to show that this polynomial p, whose value is equal to the cardinality of A, must be a constant. We observe that it suffices to show the following statement, that the value of P of Q is equal to P of 0 for any prime number Q. It suffices to show this. Let me give it an asterisk. Why does this suffice? This is because this will imply that the polynomial P of x minus constant P of 0 has infinitely many different roots, namely primes. There are infinitely many different primes, and you plug them in. If this is true, then this polynomial will have infinitely many different roots. However, a non-zero polynomial can only have finite many roots. So this contradiction will force this p of x minus p of 0 to be 0, which means p must be a constant. That is why it suffices to show this statement with a star. To show this star statement, in my opinion, the proof I'm going to present from now is the trickiest part in the proof of this problem. So pay attention. To show star, we recall our assumption that P of n is the cardinality of A of n for any positive integer n. So this is our assumption. In particular, P of q for prime q is equal to A of q. But now recall our claim 1. Our claim 1 says the cardinality of A of n is the summation of B of k's for the divisors k of n. So this guy will be equal to, since q is a prime, this is the sum of the cardinality of B of 1 and the cardinality of B of q. So this is by our claim 1 and the fact that q is a prime. Next, we're going to show that the cardinality of B of 1 plus the cardinality of B of q is congruent to P of 0 mod P. We'll prove that their difference is divisible by P for any P prime. It follows from here that this P of q must be congruent to P of 0 mod P for any P, any prime P. Because P is arbitrary, this means P of q and P of 0 must be identical, which proves this star statement, since q is arbitrary. Okay, so how do we prove this? To show this, we're going to use our claim number 2. For any P prime, we look at P of PQ, which by our assumption is A of PQ. And again, we are going to use our claim number 1 to break this down. Into, now because PQ are both primes, so there are 4 parts. Okay, now let's look at these 2 parts. These 2 parts are divisible by P. This is what our claim number 2 is talking about. K divides B of K for any K. So it follows that this is congruent to B of 1 plus B of Q mod P. But on the other hand, since P is a polynomial with integer coefficients, we must have P of PQ congruent to P of 0 mod P. Why is this true? This is true because P of xx an xn plus an minus 1 xn minus 1 a1x plus a naught. This a naught is P of 0. And if you look at those parts, if you plug in x equal to PQ, what happens? If you plug in x equal to PQ, those terms will be divisible by P. So the coordinate of P of 1 plus coordinate of P of Q is congruent to P of 0 mod P. Here we are combining what we proved in here and what we proved in here. So this gives us this congruence. And this guy, together with this, will give us this star statement. So P of 0 is equal to P of Q for any prime Q. So as we discussed above, P of x must be a constant. And we finished the proof. We are done.